Bismillahirrahmanirrahim. Today we'll talk about transition graph. We have already discussed finite automata. We have already discussed deterministic finite automata, non-deterministic finite automata, and the type of non-deterministic finite automata, which is NFA with and without epsilon move. Today, inshallah, bismillah, we'll discuss about the transition graph. A transition graph we can abbreviate as TG is basically a collection of three things. Like the previous diagram, it consists of, initial state or the start state and the final state. Here it consists of at least one start state and maybe more than one. And at least one of which is designated as a start state. So at most, there is no limit. And some or maybe none of which is designated as a final state. Keep in mind, girls, if there is a finite automata in which all the states are non-final states, yani there is no final state, in that case that particular finite automata will accept no language. And here you can see we have an input, okay, so of all possible input letter from which an input strings are formed, and a finite set of transition that will show from one state to another based on reading some specific substrings, yani even possibly the null. Here the null is allowed, yani epsilon move is allowed. We can have more than one initial state, empty string is allowed, and machine can read more than one input at a time. So it is possible that even single string, it is possible that even a single letters, and it is possible even two or three letters. So clause 3 in the definition means that every edge is labeled by some string or strings of letter, not necessary only one letter. So far in all the diagrams that we have discussed, it consists of single letter. Here it might have one, two, or three. What is a successful path? It is actually the same thing like the previous diagram, a series of edges forming a path beginning at some start state and ending at the final state. So those diagrams that does not have a final state, it means it will have no successful path. It means it will not accept any language. In transition graphs, as you know, we can, the edge consists of more than one, letter. So they have relaxed input condition. It can read multiple characters before making the transition, and every edge can be labeled with a substring instead of the single letter. And it can have multiple start states. So far, all the diagrams that we have discussed, none of them have a multiple start state. Transition graph has a multiple start state. There are two different ways in which the input can be rejected. One of the thing is when you start tracing the path, you reach to a non-final state. And another thing is it could crash while being processed, because if it has a lot of loop, it might be possible that it could crash. Every finite automata is a transition graph, but the converse is not true. Why converse is not true? Because in case of transition graph, those transition graphs that has more than one start state, it means those are not the finite automata. Those transition graphs that has even null strings, those are not the finite automata. And even those transition graph in which there is more than one character written are also not finite automata. That's why we can say that every finite automata is a transition graph, but every transition graph may or may not be a finite automata. Finite automata is deterministic because there is a unique path. However, the transition graph is non-deterministic. The ultimate path through the machine is not determined by the input alone. What we need basically the human choice as well in order to find, because it might be possible that you are in one of the state and here you are in, for example, another one. So it is possible that when it is A, you might be in Q0 and you might be in Q1. Because of this non-deterministic nature, it sometimes what we need a human choice became a factor. Here is an example of a transition graph of the language having 3 times A or 3 times B. So you can make it like this, having one initial and one starting state. Here you can see the edge is labeled with three character, and you can even make it by using two initial states. Both the diagram is the same thing. Let's assume what we did, we have a language, and here we draw an NFA of all the strings 3 times BB, and 3 times AA. So there is basically what? This is basically an NFA. We can call this particular diagram as well as NFA, and we can call it as transition graph. However, this diagram is only known as the transition graph. We cannot call it as a finite automata or NFA. Construct a DFA and the transition graph. Here is basically a DFA, and here is the transition graph. For the language that contain, here this language basically contain empty AB, BA, ABA, and AB. In this case, what we will do, we will start first of all with the least, length, as what I explained in previous diagram as well. Here, empty. So that's why what we did, we make Q0 as initial and final. Then we will take this one with 2 length. Here you have A first and then B, and then B first, then A. So what we did, we defined 2 paths. One is for the A, another path for the B. So we have here defined 2 paths. This is for the A, this one is for the B. For the A, the next one is B. Okay, and here we make it as a final state. Same is the case here. This is B, and the next one is A, and we make this one as a final state. So this is related with this one, having A, B, and then A. We define another path here for A, and we make this one as a final state. Similarly, for this one, this is related with this one. So BA, B. We have defined another path for B, and we make this particular state as a final state. So for those, because as it is a DFA, so it is required that we need to define the path for each and every input. So for Q1, path for A was missing, so we make a trap and put it here. For Q2, the path for B was missing. For Q4, the path of B was missing. For Q5, path of A, and for Q6, the path of A and B, and similarly for Q3, the path of A and B. For Q7, we need to define also the path for A and B. So this is basically what this is the DFA. If we need to make a transition graph, it is very simple. We just need to make 2 states, Q0 and Q1. And here we actually write AB, BA, ABA, and BAB. For empty, we make the initial state as the final state. So you have seen that making a transition graph is far, far easier as compared to making the DFA or NFAs. This is another example, okay, of you can here we need to first see, is it an NFA or is it a DFA? For Q0, you can see you have a path for B, you have a path for A. Q1, you have a path of A, you have a path of B. For Q2, you have a path for B, you have a path for A, even for Q3. So this is what this is. This is the way how you make a DFA, and this is the way how do you make a transition graph. You only make Q0 and Q1. Here you have ABA, and you put a loop of AB here, and you put a loop of AB. Here is the transition graph that accept nothing, not even the null string. So this is an example. I can also call, for example, I will make this as an initial state. Okay, and I will make another state. Here may be A, here may be B, here may be A, here may be A comma B, or even AA or this thing. So this one is also a transition graph, except nothing. Why? Because in this diagram, there is no final state. So construct a transition graph that accepts only the null string. So you can see here, your initial is the final. Even here, your initial is the final. This one is basically what? This one is basically a trap. Here is construct the transition graph that accept empty. So what we did, we actually 3 times A, 4 times B string. So what you did, here is my initial state. Okay, you can even make for the initial as well as the final, and then it will be accepting the null. And then you have make another initial state, because it is possible in transition graph having multiple initial states, 3 times A, and again having another initial with having 4 times B. We can also make the same diagram, like having one state with initial as well as final, and then here we will have this one, and then again we might have another state, okay, and here we will make it as final with 3 times A, and we might have another even final with 4 times B. Okay. Construct a transition graph. Let's see another example where you must have A, B, A at the end, and in the start having any occurrence of A's and B. So you can make here A, B, A, and here any occurrence of A's and B. All the words that start and end with the double letter, okay, and in the middle it might be a loop. So these are some of the examples containing a double letter, and in the start and the end you might have any combination of A's and B. Consider here, beginning and ending with a different letter. Here this you can call it as a NFA as well as the transition graph, having here different letters starting with A, ending with B, starting with B, ending with A. Here starting with A and ending with A, starting with B and ending with B. Finite transition graph that accept all the language of the words in which A occurs in even in the clumps of 3. So whenever A occur, it will occur 3 times, and that ends in 4 or more B's. So here, the thing is, you will have, whenever you will have B's, you will have 4 B's, and the A is actually 3 times. But whenever B will occur, so that's why, when you might have 3 times A in the start, and then you will have 4 times B, and then whenever again, if there is after B again A, so whenever it will be B, to the final path, it will be 4 times B. Here is an example of even. We already discussed even in the previous time, having even number of A's and even number of B's. So this is because 0 is also an even number. So your initial is the final state, and it might be 2 times A, 2 times B. And here it might be A, B, because the thing is why it is written A, B, and B, A, because if we will follow this path, so one time A will cover from here, another time A might, one time A might be covered from this part, either this one or this one, and another A will be either covered from here or here. So this is basically a diagram for having even number of A's as well as even number of B's. There is another type of graph which is known as generalized transition graph. You have seen that we will use these diagram in the Kleene theorem. So a generalized transition graph, we call it as GTG, is a collection of 3 things. Okay, here a finite set of states of which at least one of them is a start state and some or maybe the final state. An alphabet epsilon of possible input, directed edges connecting some pair of states with the each labeled with the regular expression. But the final, keep in mind, but the final transition graph always consists of one start state. When we do the conversion at the end, it will have one start as well as one final state. So this is basically because in the case of transition graphs, you have multiple final and multiple initial states. But when you do the conversion in the generalized transition graph, one initial as well as one final. So you have here Q0, Q1, Q2, Q3. Here basically it represents the statement, which is what? Which is basically BC, starting with BC and ending with BC and having any occurrence of A's. So this is basically is an NFA. Why NFA? Because for Q0, the path of A is not defined. For Q1, the path of A and as for Q0, path of A and C is not defined. Q1, path of A and B is not defined, and so on. Here is the transition graph, and here is the generalized transition graph for the same expression. That's all about the transition graph. Inshallah, in the next lecture, you will see Kleene theorem and you will see the use of and the benefit of the generalized transition graph. Thank you very much.